All right. So we spoke a bit about what the divide and conquer approaches could be for the problem statement of uh, getting the ticket counts from South Zone and Goa. And we spoke about two approaches in the previous video. The first was the brute force approach. What I call as brute force is because you're just taking the data and transferring it across, and so that's not the right thing to do because it's very expensive. We spoke about how the different resources available in a typical machine have their own latencies. The approach number two was more intelligent because we didn't use the part of the machine which is the weakest, which is the network. Instead, we leveraged the CPU and memory more by making the functionality of count a little bit more complex, right? Instead of just simply counting one final answer, we made sure that we counted South and Goa separately for the same machine. Did it for both the machines, and then once it was done, we got the final answer by just summing up the counts. Now, this kind of process is what's called as the planning, scheduling, and execution of a divide and conquer algorithm. So the planning is what is responsible for figuring out how do I break down the problem statement into smaller problem statements which can be run in parallel. Now, notice that the more embarrassingly parallel a problem statement is, the less dependence I have on the lesser, on the machines needing to talk to each other. So, what I mean by that is, if two Python programs can run on two machines completely independently without needing to exchange data, that's the best. The moment data exchange needs to happen, then the volume of data becomes a factor, network speeds become a factor, etc., etc. So, by taking a problem statement at the top level, dividing, conquering, dividing, conquering, dividing, conquering, you then create a tree of problem statements which are smaller. Each of which, if you solve, you get to actually um, uh, get to make further progress on the top level problem statement, right? That's the essence here. So, what do we need to do here? We want to be able to plan the approach of solving for the top level problem statement by making incrementally smaller problem statements, which are ultimately going to be solvable using embarrassingly parallel computation. So, if you look at it as a tree of sub-problem statements, the final level of the problem statement can be solved completely embarrassingly parallelly, meaning it can be done independently without needing any exchange of information. Once that's done, then you roll it up, then you roll it up, then you roll it up, and go up the tree. So that is the planning activity. Once the plan is made, once you know exactly what you want to do, then you have to be able to schedule it. Scheduling here is important because there is a dependency to the jobs, right? Which means in a tree of problem statements, you can't solve for the top level problem statement until the sub problem statements are solved for. That translates into a schedule of activities, each of which is going to be tracked based on its dependencies, based on prerequisites, and what is it feeding into. Once that scheduling is done, then you can start executing it, starting from the lowest level all the way up. So a typical divide and conquer tool, or should I say, a typical divide and conquer implementation will have these three elements as critical. So that's the first concept we're going to spend some time on. MapReduce, let's talk about that. MapReduce is the first of the implementations of divide and conquer that was applied for big data. Now, before Google published this MapReduce concept, there was already the concept of MapReduce as a mechanism of expressing functional logic in a programming language called as Lisp. And that was quite popular back in the day meaning 70s, 80s, 1970s, 1980s, right? Um, and then, for various reasons, Lisp didn't become popular. And over a period of time, the concepts associated with Lisp were very powerful, and those concepts naturally made their way into lots of other things, like design of other languages and so on. One of the places where it did make a way and inspired technology is MapReduce, right? When Google came up with its Google MapReduce paper. So MapReduce is actually an example of divide and conquer. Um, in a sense, MapReduce is a parallel programming framework which implemented divide and conquer in its philosophy. It allowed for any programming language to be used. Python, Java, shell scripting does not matter, right? It allowed you to harness the power of hundreds to thousands of CPUs spread across multiple different types of machines. And most importantly, it optimized for being able to solve problems at massive scale um, by relying upon clusters of machines and their storage, right? As opposed to uh, relying upon just memory. And I'll talk about why this distinction is important. But in a sense, when MapReduce first came, it said it's most important for me to make progress when a problem statement is large at scale, when the data volumes are extremely large. Why? Because the state of the art at that time, if you go back to that first video, was supercomputers was the only other option that you had, or you had to buy really expensive proprietary databases, right? And those were super expensive. And what's important is that all the other approaches that were attempted could not deal with the failures that were possible the moment you didn't buy expensive hardware. Like if you just used simple commodity hardware, cheap hardware, because the failures are common, uh, cheap hardware fails more frequently, right? Disk fail, memory fails, etc. Um, if you didn't know how to deal with that failure well, then if you were in the middle of a computation and a failure happens, too bad, right? You just have to start all over again once the failure is fixed. And imagine if that kept happening, right? The bigger the cluster, the more the chances of failure at any given point in time. Then you would never make progress. You'll just keep failing and the program will start again, fail, program will start again, etc. Becomes extremely, extremely frustrating, right? To then get any kind of answer out. So what MapReduce did, or rather the designers of MapReduce did, was to say that I'm not going to be, hampered by failures of the machines. Instead, I'm going to make my design in such a way that even if failures were to happen intermittently, I have a mechanism of resuming from where I left off, right? So if you look at what that meant, it means that you need to be able to know that you have done work up to a certain point in time, and you need to be able to reliably pick up the work from that point in time, even if something were to happen. So, the count of 1 terabyte, as an example, if I've counted 500 gigabytes, I've got 50% more work to do. And if I store this information somewhere, such that even if there's a failure, the failure could be the machine failing, the machine rebooting, somebody accidentally tripped on a power cable, right? Or the CPU going bad and you replace the CPU and come back, right? In that kind of a scenario, you've done 50% of the work, you've stored that information somewhere, right? I'll come to what that somewhere is a little later. And then the failure happens for whatever reason. The machine comes back up after the failure gets fixed and now it's running again. You need to be able to pick up from the 501st gigabyte, right, all the way to 1 terabyte now, so that the remaining 50% of the work can happen. So that kind of a design pattern is what MapReduce from Google optimized for. Basically, it's more important to make progress at massive scale than to worry about whether I'm using memory or whether I'm using too much CPU or not, right? It didn't optimize for memory, it didn't optimize for the CPU, it optimized for being able to make progress. What MapReduce really uh, did is open the eyes of how such divide and conquer implementations can be done at large scale. Because for the first time, Google was publishing live research that was extremely applicable, very practical, and they hit the nail home, right? Which with respect to what are the problem statements you would see at large scale, and how do you deal with it? How do you solve for it? So three problem statements. The first is how do you do parallelization at very large scale? It's impossible to have a human track that. We had these instances of two machines, one Python program in each. If a human was actually going to that machine, logging in physically, then doing /Python and executing the name of the file, that's one way of doing it, right? But if you had 100 machines like this, It's impossible, right? I mean, rather, it's possible, but it's impractical, right? For a user to go log into each of those 100 machines one by one, do dot slash Python, and then run the name of the file, give the name of the file. Why is it impractical? Because it's just very painful to go log in and do it. The other reason why it's impractical is how do you, I mean, what do you do when there's something fails, right? You just go back and run it again, becomes a challenge. So the parallelization has to be automatic. What's more important is that we're talking about not just embarrassing the parallel tasks, but tasks which are solved using divide and conquer, which means it's a tree of parallelization, which means there is dependencies, the scheduling, and all of that. So all of that needs to be taken care of as part of this automatic parallelization. The second angle here is how do you deal with failures? You deal with failures by doing what I said before, right? You just store in some place how much work has happened so that you know how much more work needs to happen and where it needs to pick up from. So that ability to deal with failures was very, very interesting and very critical for why MapReduce was successful. So the fault tolerance capability, that's what it's called as fault tolerance. The third angle is I need to be able to know whether I'm making progress. If I know I'm not making progress, then I could just be twiddling thumbs and waiting for something to happen. Whereas in reality, what could have been happening is the program's just starting all over again, rebooting, nothing's making progress, nothing's happening. So can I get status updates? And can I know which resource is subject to what kind of load, and whether the resource is actually healthy, right? If there's a failure that's happened, can I know about it? Even though I have like fault tolerance built in, but if I know that a failure has happened, I can go fix it. So monitoring and status updates was a very critical capability. Prior to MapReduce talking about this, everybody knew monitoring was important, but it was more a nice to have, right? Because in the worst case, what could happen is you just have a human go to the data center and look at the machine and say, oh, okay, the machine is operating fine. Now, if you have hundreds of these machines, anything could happen to any machine at any point in time. Physically having a human to go check on this is just completely impractical again. So monitoring was a critical requirement, and MapReduce brought that up. And status updates was a critical requirement because when you operate at very large scale, some of these problems are not going to be solved in seconds. You're going to have to run algorithms and programs for 30 minutes or 1 day, right, or 7 days. So in that kind of a setup, um, if I know it's going to take a long time, but if I wait for 2 days and then figure out, oh, something's gone wrong, I have to start again, that's very painful, right? That's 2 days wasted effort. Instead, if if the program itself, if the paradigm, if MapReduce itself can publish what is the progress I'm making in terms of the data volume I'm reading, in terms of the processing, then it's very helpful to know, okay, yeah, I mean, I still have 60% more to go, I have 40% done, etc. Right? So that status update is a critical part of measuring progress so that you know that you're not waiting forever. All right. So what did MapReduce, what was the design for MapReduce? The first is map function corresponds to a certain way of compute. I'll talk about that in a minute, what it comprises of. Then it had what's called as a reduce function, which is a counterpart to the map function. And once everything was done, the results were available. To make all of this work seamlessly, you needed to have a scheduler. The scheduler is responsible for figuring out which tasks run where and how are they connected to each other, etc. And then finally, in order to exchange data between two tasks, right, a map task and a reduce task, you need to be able to shuffle data across. Shuffle meaning you just move the data, transfer the data across. Notice that I said that we need to be able to transfer data between two tasks. I didn't say machines. That's because the task is the unit of parallelism, not machines. Why is that the case? Because some of the machines are really powerful. Like some machines could be having 10 CPUs, 100 CPUs. In which case, it has the capability to launch and manage multiple parallel tasks at the same time. So let's take the first machine example that we spoke about, two CPUs, 1 TB of storage space, having South Zone data. Even if it's two CPUs only, I can still run potentially not just one task, but maybe three tasks, right? Two tasks, three tasks. Why? Because I have two CPUs, firstly. Secondly, the CPUs themselves do what's called as context switching. They have the ability to manage slightly more number of tasks as well, not a problem. And they can just make it work. And uh, the reason why it works is because sometimes the task is waiting for storage, right? And storage is busy servicing one thread. In the meanwhile, the other thread can actually start doing its processing because it's already received its data. So those kinds of context switching is all possible. But any which way, even for those two CPUs, I'm talking about at least being able to do two tasks, if not more, on that machine. So I don't need to be limited to one task. I could run as many tasks as there are possible in a particular machine. So if there are multiple tasks to run on a single machine, then I need to be able to schedule it. I need to be able to work with it. Now, since multiple tasks are possible in a single machine, the task becomes the unit of parallelism, not the machine. So, in which case, two machines in the cluster translates to potentially 20 tasks that are possible at the same time, or 5 tasks, or 10 tasks. Like it depends on the capacity of the machine. So, yeah, so map tasks become the first set of tasks that run, and as you see in the way this is depicted, one top order problem statement is divided into multiple map tasks that run parallelly without talking to each other, right? So there's no arrow that connects these red boxes with each other, which means this is an example of a embarrassingly parallel computation, right? I'm just taking a map task, which means the same copy of the code that does this map operation runs on every single one of these tasks. I'm doing that out. I'm doing that execution. Once I get the output, what do I do with the output? I shuffle. I shuffle based on some algorithm, some kind of a logic. I'll talk about that in a minute. Once I do the shuffle, then I spin up a bunch of reduce tasks. What do the reduce tasks do? They aggregate data. They collect data and do some aggregation on top of it. So the collection action is shown by, you see all these arrows converging here, all these arrows converging here, etc. So that collects the data together in that one task. And within the task, it does a certain operation, which is typically an aggregation. Aggregation meaning a grouping of items together, a collection of items on which you do some kind of an operation. So that's reduce. And these reduce tasks also, if you see, there is nothing that connects them between each other, which means they're also embarrassingly parallel. So same copy of the reduce code running on multiple tasks on multiple machines and running in parallel to produce the output. What output does it produce? It produces the final answer. So one problem statement can be broken down into a map followed by a shuffle followed by a reduce. That's possible. That's the minimum implementation plan, right? Think of it as this is actually the plan. The most sophisticated plan that's possible is I could have multiple levels of MapReduce, which means map shuffle reduce, or map shuffle reduce, etc., right? So it depends on what is the nature of complexity, what am I trying to solve this problem, but I could chain multiple map reducers back to back. That way I get the ability to do really complex problem statements with really multiple levels of hierarchies of sub-problems and I'll still be able to solve for it and get the final answer. Great. Let's just talk about shuffle briefly. Shuffle is responsible for getting the right data to the right place, meaning a map that produces output of a certain kind tells shuffle that this is the output I have and this is the way to interpret the output. And the overall planning of MapReduce, right, for that particular problem statement would have told shuffle that you need to look at that data, pick up certain aspects of the data and move the data there to this other machine. Likewise, move the other data there to this third machine, etc. Right? That's the logic of shuffle. So for the Goa South Zone example, I would have in the first approach where I'm moving data, remember, the map task just plainly reads data, nothing else it does, right? There's no processing that happens. Rather, there is no functional processing, meaning there's no operation of the data that I need to do to change the data. I just read the data as it is from the disk. Once I do that, then I ask shuffle to only take South Zone data, or rather Goa data in the first machine space, and put it into machine 2. So I'm giving it a key. The key will be which field corresponds to Goa South Zone, right? Usually it's the city of booking. And I'm in that key, I'm saying for Goa, put it to machine 2. Likewise, in machine 1, the shuffle function will have a logic that says for Pick up the city key or the region key, and for value equals south zone, put it in machine one. So shuffle needs to look at data individually, makes a decision on which machine that particular data is going to go to, and then transfers the data over there. Yep. So a map task is like a reduced task. The only difference is that the reduced task has aggregation functionality built in. Right? You could still use a reduced task and not do aggregations. That's up to you, right? But it's got aggregations built into the interface. Map task does not have aggregations built in, but in both cases, they're embarrassingly parallel. They just run as it is on every machine in parallel without dependencies. The only dependency is being is actually availability of the data, which is being satisfied by the shuffle operation. Great. So I'll pause here. This is a logical time to just pause on what MapReduce is. In the next lecture, we will actually take a look at Spark, which is the next example of divide and conquer.